That's me whenever I have plans the next day. I'm like, oh, well.
Yeah. So before the break, we were looking at
Gotta wait till next.
What's that, Tyler?
Oh, it must have been my internet messing up and making robot sounds. No worries.
Okay. Okay. I thought you had said something else, and I couldn't quite catch all of it. So before the break, we were looking at functions, reusable code, and an expansion on variables. We saw variables where we would store a data point. The next step up is, well, a single data point isn't the only thing we can keep a reference to. We can keep a reference to an entire collection of instructions. And before the break, we quickly looked at the keywords we need for that in Python to define a function. And we either just do stuff, in which case we call it a void function. We do stuff and then it's done. And when we need those instructions to run, we just ask for the name we put there. Or we have a return function where we do stuff and we end up with the value that we want to send back to wherever that came from. And kind of the same thing, we just ask for that name of that function, once again, in order to run it. But if it's returning something, we have to put it somewhere. So when we go to put together our flowcharts here, we have the same functionality. And we've kind of seen some of it. When I right click, we have a couple words here, subchart and procedure. You will need to come up to the menu and go to mode and make sure you're in intermediate mode. You don't want to go to object-oriented mode. Object-oriented mode, you have a whole bunch of other steps that you have to go through first. And yeah, there's a whole bunch of other steps that you have to go through first in order to set things up. So we'll need to go in there. So come up to mode and make sure you're in intermediate mode. Oh, I don't need to save this. So make sure you're in intermediate mode so that you have two options. In Novus mode, you'll only see an option that says add subchart, which is a little different. So maybe I'll start with that. So we saw subcharts before. I don't know, I'll make one called double. It gives us another flowchart here. Over in the main, I'll set a variable, just set X to some number.
So what are we doing with this Raptor program here?
Just going through some basic concepts on it.
Oh, nice.
Showing some points. We'll get to a definitive example soon.
Yep.
Just showing what some of these things do. So with subchart, we can set a variable and then we bring in a call statement and ask for that other subchart, say double, and over here, well, I'll just do an output. I'll say print 2 times X. The key thing is that X was not defined on this chart, right? I set up that variable X on the previous chart. When I run this, it does still know what X is. It took twice as much as that value and output it. So really, when we have a subchart, what that's doing is reorganize our stuff. That's just taking a section of the flow chart and drawing it somewhere else to make our stuff more cleaner and organized. It's not a separate thing. I'm going to go ahead and delete that one. Well, I'll just leave it there. I'll ignore it. That works too. A subchart's a little bit different. We create a subchart, or sorry, if we create a procedure, we get this little box that we have to set up a bunch of things. some of which might look familiar from the things we were just looking at. We need a name to refer to this procedure. And then we have a bunch of parameters. Some things coming in as inputs, and the checkboxes should be obvious. Some things are inputs and some things are outputs, which means they're going to be return values. So I'll set up kind of the same thing. I'll call it double. We'll take in something called number and return something called 2 times. So we set up our parameters and define whether they're inputs or outputs. I'll call it double number. It's not going to let me use the same name twice. So I'll give it some sort of name we can refer to it by, set up our parameters, whether they're inputs or outputs. And we got another flow chart, but you'll notice our start bubble looks different. It's expecting things to come in and go back out. Whereas on the other one, or the other two really, our start bubble just starts running. It's just whenever it gets there, it just starts running. And there's nothing else to do. So if I tried that same thing here, print X, output X, and set X to that same value, X equals 4, and then called that other tab up here that we just made. Well, it's expecting 2 things. I'll send in a couple variables, X and Y. Now when I run it, when it jumps over here, it doesn't know what X is. So with the procedure, it's completely separate. The subcharts just draw a part of our chart somewhere else to make it nice and clean. The procedures are the ones like functions. It's something completely separated off. So we can't use any of the variables we had over here. We have to make new ones, which is our parameters we send in. So we can do an assignment here. Set that 2 times variable, the thing that is getting returned, to 2 times our number. And then when we get back here, well, I'll just run this like this and point it this way. Notice over here in the watch window, it created a thing called Y. This function is a return function. It does some stuff and then sends a thing back. So here in the call statement, look at the predictor text, it's saying what number is going in. So I'll pass in what's stored in that variable X, and then what is coming back. So whoops. And what's coming back, I'll put in a variable called result this time. And then we can print the result of that, I guess. Just a simple thing to kind of show that syntax. Yeah, nothing fancy there, just kind of showing that subtle difference between the subcharts and the mod and procedures over here. The ones we want to use are going to be procedures. We don't have to have any inputs or outputs, right? I'll make one like that one we did in Python. I'll make one called say hi. Doesn't take any inputs, so just leave these blank. Not going to send any outputs back. Is the result of what this does is just print the words hello world to the screen. So I'm going to go to call that. And again, when we ask for a function to run, we call it, which is one of our shapes here in Raptor. So we'll call that say hi function. And notice that when it predicted it needed the parentheses.
I have a question.
Yes.
So my project that I'm doing is poetry, right? And so I just want to know, like, how could you preset text and then put in the, already have the text available so
Oh.
that when you could put in like words to like, do
So
that.
there's going to be lots of ways to deal with that. So that's one of the main points of your project is figuring out a way to deal with that with the tools we have.
Yeah, for the tools that we have of just presetting text beforehand, right?
Yeah.
So like that's like ready to go and available. And then just putting in the blanks.
So
Just
part of the project there is part of the bulk of the project really is figuring out a way to do that.
Yeah. To just putting in the blanks and telling people like.
Yeah, so that's a question that I'll try to avoid directly answering because there's lots of ways to do that. So the point of the project is I want you to figure out a way to do that.
Okay.
And develop that program. If you get completely stuck, I can help with it. But yeah, that's this subject's about problem solving. So in your case, that's the problem you want to solve. Probably not the answer you wanted there, but that's what you're trying to figure out how to do. Use these few tools we have, because here in about 25 minutes, we will see the last of our tools. And then you'll have all the tools needed to do that, Keegan. You just have to figure out how to put them together in order to do it.
Yep.
There's lots and lots of ways. There will probably be some trial and error figuring out what the best way to do it is. But you've seen ways to store things and the different instructions, how to put things together. So you just have to figure out what the right way to step through those tools we have, to apply those tools we have in order to do that is. Because here in about 20 minutes, we'll have seen the last of those things. So that's the quick pass on syntax on those. We'll start using them regularly, but it's essentially the same thing we've done. We've already been writing programming instructions. The difference with functions is we save some of those instructions, not a full program, just a couple of instructions that we're going to use repeatedly. We save those to a reference value, just like we were saving numbers to a variable before. And then we can ask for that over and over and over again. So we'll see it, but that leads us into the what machines are capable of doing in order to produce that some sort of repetitive structure. We want to do things over and over and over again. So I'm going to go through something here that I'm gonna go through it. Some of y'all will see this before long, and there's an easier way we'll get to in a moment. But first off, I want to talk about something natural to the machines. One more of our four constructs to look at. That's the reiterative structure. And let's start with just a familiar situation here in America that I know everybody has encountered at some point. Say we have some person, maybe a singer. Some singer, they got their microphone there. So when they start singing, their voice comes out of their mouth, goes in the microphone, down a wire where it's going to get amplified and come back out of a speaker, right? A little bit louder. And if things are set in a certain position, that sound is going to go right back into that microphone. Down the wire, get amplified, come out a little bit louder. Right back into the microphone, and that process is going to repeat, and it's just going to keep going through, getting amplified, back into our input, come down, get amplified, and that output goes back into the input, and before long, the room's just filled with a big screeching sound. Everybody's experienced that before, right? It's a really, really common thing in America. I'm going to erase that picture because by the time I finish that picture, there's not really anything indistinguishable there. But the situation of audio feedback. Typically, that's an annoyance, right? We don't like when that happens. Happens quite a lot on Zoom calls, right? There's microphones and speakers on the machines, and sometimes the output goes back to the input. But it's not always an annoyance. A number of musicians have just learned to use that. Especially guitar players who have an instrument that reaches really high notes anyway. Tom Morello is one that always pops in front of my mind, but he's one of a long list of people that learn to control that feedback really, really well, so that it's just another note that his guitar plays. Or in Tom Morello's case, he would sometimes unplug his guitar and just use the cable and the feed, and was able to get feedback from the cable. But that's beside the point. He was able to use it like it just became another note. He was able to control it. And that is what is natural to machines. Feedback, where output goes to input, is what's natural to a machine. Or to put it in pictures, there's some sort of input that feeds into whatever our processing is, whatever sort of processing our machine's going to do, and then that heads over to the output. But instead of going back to a user or feeding into a different machine, that output comes right back over and feeds back into the original input. It's a very important thing in machines. As Americans, we're mostly most familiar with audio feedback, which is usually an annoyance. But this is a very important thing machines are capable of, sending their own output back to their own input for repeating things. This is what machines do naturally for reiterative structures. And when we're programming, we can take control of this and use feedback loops in order to repeat sets of instructions, in particular a function. Right, we just saw a function call. So I'll draw the little pictures up here. That's a quick way to do it. So we have some function that goes out, does its stuff, comes back, and then what it's going to do is it's going to call itself. Maybe I'll draw the arrow over here. When it goes out to do something else, what it does is call itself again. So then it can just keep doing that over and over and over again. And we take control of it, kind of like those examples I use with audio feedback, where for some musicians, that's just another note their instrument makes. Makes a great way to end a song sometimes, right? When the band's finished and they just throw the microphone down, walk off stage, and the climax of the song is just the feedback when the mic starts feeding back at the end. It's something we can control and make use of. And when we do this in programming, it's called recursion. The thing is, recursion can be a little difficult. We have some criteria, because machines are very rigid things, right? They're just repeating patterns. The machine is just it's a non-intelligent item with electricity flowing through circuits, and that electricity is, some of those circuits are able to turn other circuits on and off, so it creates a pattern. And then all that stuff that we talked about, that was things humans have done with that pattern. The pattern itself doesn't have any meaning. So if the machine's already built, we have some restrictions on how we can do things. So with recursion, there's certain conditions that we have to meet in order to use the repetitive structure that comes naturally to the machine. The problem, I should stand on this side so the camera sees what I'm writing. The problem must reduce to a simpler version of itself, a smaller version of itself. And I have an example where this stuff will make more sense. Is if the problem's reducing to the same problem, that really doesn't sound like reducing. So we'll get to an example that'll help clarify that here in a second. This reduction must eventually stop. It can't reduce forever. So the problem has to reduce to a smaller problem that is a smaller version of the exact same problem. And that reduction has to eventually stop. Eventually reach a base case. I'll say it like that. Has to eventually reach that base version, the smallest possible version of that problem. And 3, the solution has to refer to itself. So whenever we can meet those 3 criteria and to refer to itself, that's what's going on up here in this picture. We call a function, but then what that function call does is call the same function. So that function calls itself. So it just keeps doing that over and over and over again until it hits some sort of stopping point.
Yeah, so it's like driving itself insane then, just like, continuously just over and over again.
Yes. Well,
That's what the definition of insanity is. That's the definition of insanity, just driving itself insane. It just keeps calling itself and itself tries to go on, but it can't because it's still making the same decisions over and over again.
Exactly. That it would drive any human insane. That could also be the definition of a good machine. If it does the same thing over and over again forever.
Yeah, but in terms of
usually our machines mess up at some point when we ask.
Yeah, that would be annoying, and then it just would crash out. It continues to do it over and over again. Then insanity, like I said, and then insane. Creates not it's in scenarios for any computer human.
Yeah, exactly. The thing is, we have these strict criteria.
Yeah.
Not all of our problems fit this criteria, right?
Right. Plus, there's different solutions for different.
Some problems can't reduce all the way down. So these are.
Right.
So one of the things with doing recursion, what machines do is, well, for one, we can't solve every problem. Sometimes we have to modify our problem, find the solution for that, and then turn that modification back into the solution we wanted for the original. Sometimes we have to solve, because at one point this is all we had on machines, and then we'd have to solve we might have to solve a different problem entirely and use that solution to try to figure out a solution to our original problem. So there's a lot of back and forth, not everything fits this, so it's really hard. So we have an easier way to do this we'll get to in a moment. But before we get there, a quick view of this, because Also, this is what machines do naturally. So this is better for the machine and better for the machine means it's going to happen a lot faster. So it's good to do this when we can. A really good example of a problem to solve this way is factorials. I was going to do a quick factorial example to kind of show the process here. Has everybody seen that? Anybody seen factorials? That just seemed like a really strange word. In your math class, you may have seen an exclamation mark. Some people will see it when we're first learning to multiply, only up to like small numbers. Third or fourth grade, just showing that something exists. For most people, it doesn't show up to calculus 2. But 5 factorial is really, that means 5 times 4 times 3 times 2 times 1. And obviously, the times 1 doesn't do anything. It just doesn't make any sense to stop our pattern at 2. So it's the number we're concerned with multiplied by every number smaller than that. So 5 factorial is 5 times 4 times 3 times 2 times 1. Or 8 factorial. 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So the number multiplied by every number smaller than that. I'll write the generic version of that here in just a moment, because this is a problem. It's a math thing. Most people don't see it until calculus 2 anymore. But it's a math operation we can do. A unitary math operation only takes one number. Like, what number do we want to take the factorial of? We don't need a second number like we do for addition or subtraction. And if we check our criteria here, the problem must reduce to a smaller version of itself. So 5 factorial is 5 times every number smaller. That every number smaller. 4 times 3 times 2 times 1. That would be 4 factorial. So another way to say 5 factorial is 5 factorial is 5 times 4 factorial, which is 4 times every number smaller. Well, I'll leave it there. Then 4 factorial is 4 times 3 times 2 times 1. Again, that every number smaller part, that's the next factorial down. So our problem reduces to a smaller version of itself. 5 factorial is the same as 5 times 4 factorial. And 4 factorial is 4 times 3 factorial. 3 factorial would be 3 times 2 factorial. And eventually we do hit that base case because we're only walking down to 1. There's a technicality, 0 factorial is defined to be 1. So in math class, you'll see that written with another times 1 at the end, which represents 0 factorial because of that definition. But we only walk down that far. So we're reducing to a smaller version. It eventually reaches a base case. So in order to look at recursion, we just need a function that solves factorials and have that refer to itself. So we want to say 5 factorial, it takes our number and then calls the factorial function again. And again and again and again until it reaches that 1. So the generic version of it, some number, I'll write n for number. The factorial of it is going to be n times n minus 1 times n minus 2 and just dot, dot, dot for however many there is. But eventually we'll get all the way down to n minus n, which is kind of the end. We only need to go down to 1, so we do n minus n, which is a complicated way to write 0. We'll go all the way down to 0, but then we want to stop at 1. We don't want to take that last step. So n factorial is the number we're looking at times every number smaller than that. And it is a perfect thing to put together and to look at recursion because it very nicely fits these criteria. Not all of our problems do. Pretend. So yeah, we'll look at a quick example of this. Does that make sense? The math operation we need to work on? Any questions? I saw you unmuted, Tyler. Did you say something? Oh, okay. Internet issues. Yeah, sometimes the downside of it's convenient here. Yes. Machines, this is what machines do. So we always have this. It's really hard. So in a lot of our programming languages, people invented an easier way to do repetitive structures, which we will see in a moment. But this is the one we always have if we're working with a machine, because we always have feedback. Just those criteria sometimes are really hard to meet. But when we have something that falls perfectly into them and we don't have to do any modifications, kind of like what factorials do, then recursion is usually a better option. So let's do a quick example of that. I'm going to set up a function that solves factorials. So create a procedure. I'll call it factorial. And it needs two things. It needs to take in the number we want the factorial of. And then in the next row, I'll set that to output. And it's going to output, I'll say result. So the number we want the factorial of, it does the math, and then sends back a result from that. Oh, okay, yeah. That sounds like a complicated situation. But being able to, in the chat room, he is analyzing why his audio broke down temporarily. But being able to figure out what went wrong is the first step in fixing it. So we'll need a name to ask for a set of instructions that we're going to ask for over and over again, the number we want the factorial of, and the result of that factorial. So the first thing we have to check is that base case, because we eventually want to stop. We don't want this machine to do a feedback loop forever. We just want it to run through a feedback loop until it hits that base case. So almost always in these, we set up a selection structure. Oh, I got to save. Yeah, replace the other one. I don't know why they were. Oh yeah, I remember why it was there. So first, we're almost always going to have a selection structure inside of our function that we're calling, which is another one that's natural to the machine. So these things are kind of working with the machine the way it goes. And we need to know when we get to our base case. So when we get all the way down to 1, or if the user sends us something smaller than 1, like if they type in some nonsense like -7, we'll just send back a 1. That'll work. So if the number that got sent in is less than or equal to 1, so 1 should be our base case, but if the user gives us a 0 or a -12 or anything else, we'll go ahead and stop when we get to 1. And in that case, well, that's our result. Set result to 1, because our base case is 1 factorial. 1 times every number smaller is just 1, because there's not any number smaller. So that means we're all the way done. So send back the result of 1. But if it's not 1, well, then we need to call our function again. If it's not 1, then what we want to do is call factorial. We'll call this function again, And we want the next smallest one, right? What was written on the board? 5 factorial is 5 times 4 factorial. So if they give us a 5, we're going to ask for 4 factorial. Is what's going on there. And I'll put this in a variable called smaller when it comes back. So 4 factorial, if they send in a 5 for that particular example, the computer will go figure out what 5 minus 1 or 4 factorial is, put that in a variable called smaller, and then we can do that calculation that the final result we want is the number that was passed in times that smaller factorial. So if they pass in a 5, we'll ask for the next smallest, we'll ask for 4 factorial, which is smaller, and then we'll take 5 times 4 factorial. And keep it, so it'll keep going there, and then eventually it'll get down to 1 because we're asking for number minus 1 every time. So eventually it's going to get down small enough to hit that base case and then return stuff. Then all we have to do is ask for it. So I'll come back up to the main and call factorial with some number. I'll say 5 because I keep using that for an example, and put the result in, I'll abbreviate it. I'll call it fact, and then we can print that out. I'll put the whole sentence. So number plus an exclamation mark is our factorial sign is equal to whatever the computer found that to be. Notice it almost looks like our flowchart stuck. If you look over at the watch window, something's going on. Oh, that's right, I didn't have a number. Let me do this. Enter a number to take the factorial of. And put that in a thing called number. And that's what we're going to take the factorial of. So a process you all have probably seen a few times, right? We put down what we think it should be, look at what went wrong, and make little adjustments till we get to what actually works. So I'll enter 5 again. So we want to find out what 5 factorial is. So enter a 5. It goes in here, and notice in the watch window, it keeps asking for factorial. And then we get to the end, and it like piles up those requests to call that function. Then when it gets to the end, it comes all the way back down. So what's going on here is we send in a 5, comes in here. That's smaller than 1, so we go this way. Oh, well, we need 1 less, so we come back around and send in a 4. Come through. Oh, it's smaller than or bigger than 1, so we go this way. Come back around, then we have a 3. Come through, and you can see that.
Did I fix it?
Feedback loop. Yes,
Ha!
I hear you now.
Okay, it turned it down. That's weird. It literally turned it down. Okay, I'm paying attention. I was.
Oh,
it was bothering me. Yeah, thank you.
Yeah, it's good to be. It sounded like from the chat room. It sounded like you kind of knew what went wrong, but sometimes it takes a minute to find it.
Pulse audio volume mixer, best thing.
Yeah. So notice how we just keep going back through this same process until we eventually get down and pass in a 1. That time we're finished. So we come over to result, hit the end, and then end goes back to whatever called it. But that's all these loops over here on the right. I lost my cursor because it's doing the little thing. I'll switch to red. So now we go back to the caller, which is back down these loops. So come back here, and then we can proceed on down. So the first one was a 1. We come back and hit the 2, come around. We got a 2 going in. Go back to the caller, which again is these loops. So it comes back around. Where the 3 passed in, and we're like backtracking now. So that's kind of what's going on in those. Get all this ink spot out of the way, then I'll run that so we can watch it again. And factorials get really big really quick. If I go from 5 to 8, you see it keeps calling more things, and that's what's going on over in the watch window on the left. It's asking for another one, but it doesn't have anything yet. Oh, it finally found something, so it got a 1. So it passes that back, then it can do that multiplication. And it does that last step all the way back down that stack of calls that it made. So you can see 40,000 by the time we get to 8. Factorials get really big really quickly. So I do 12 factorial and maybe turn up the speed because y'all can see which way that's going. We're up to a pretty big number pretty quick. Your average calculator will probably start overflowing somewhere around 19 factorial. Let that stack build up. Our program here looks like it can handle that number. It's a really big number by the time we get up there. And if we took that and multiplied that by 20, obviously it grows it grows considerably every time. Not exponentially, because it's just the next number, but as our number gets bigger and bigger and bigger, it's going to grow by more every time.
Good
So that's
save.
the idea. That's the idea of recursion. What was that, Tyler?
That's a good save on the exponentially thing. That's usually how I describe something getting bigger and bigger.
Yeah, I almost used it as the generic English class exponential when we're doing
Exactly.
Yeah, it is a linear growth. It's just
Kind of like decimating something, like same thing.
Yes, it's a multiplying linear growth. So
Okay.
the growth factor grows, but not exponentially. Actually, factorials grow quicker than exponentials. Is it
because it's a straight line instead of a curve?
Yeah, because we're just multiplying by the next one, right? If I put
that makes sense.
X to 19 squared, 19 times 9. So here's 19 squared is 361, but 19 raised to the 19th power, that one might be bigger. There comes a point where they do pass. So let me do a smaller one. So let's say 8. So I think it just crashed. It couldn't finish.
Nice. What caused it to crash?
19 to the 19th power. Let me try 8.
Okay.
8 raised to the 8th power. So if we take 8 factorial, it's 40,000. The exponential is still bigger. But there comes definitely a point where they're smaller, right? So 5 factorial versus 5 to the 5th power. 5 factorial is 120, and 5 to the 5th power is 3125. So the exponential is much smaller there, but by the time we get to 8, the exponential is larger because of how multiplying by smaller numbers makes a difference. So definitely not the same thing. It's a different operation, but it gives us very, very large numbers very, very quickly. So that's the idea of recursion. That's what machines have in order to repeat stuff. There's a problem with it though. It's really hard to work with. Not all of our problems. That was very carefully chosen as one that fits our criteria perfectly, so that all we had to do was plug it in. The vast majority of things we want to do repeatedly do not fit that pattern. And in the early days of computing, sometimes there was problems they couldn't even solve with the repetition stuff because it would not fit this pattern. And what programmers would have to do is come up with a different problem the computer could solve and use the solution to a different problem to figure out their problem. It can be really hard to work with. Oh, is it okay?
That's the base of functions, right?
Yes, it's all based off functions and it's feedback loops. So this is what's natural to the machine. We always have a feedback loop. We can always send our output to our input.
Okay. Does that have to do with loopback plugs, you know, like in networking? Is that used there too?
Yes. A loopback is a feedback loop. Instead of you go out like you're going to the internet, but instead of going to the internet, you loop back around to your own network card.
Yeah. Okay.
Instead of going to another network card, you just go to your own network card.
And that's why it's again, like you said,
it's going across the network. Because machines aren't intelligent. It doesn't know the difference between its own network card and a different network card.
Exactly. Cool.
So feedback loops are something we always have. It's very, very important to the electrical level. But it's really hard. So in the early 60s, they developed, somebody came up with the idea and it's like, this is too hard. Let's come up with an easier way. And invented loops. Most of our languages have loops. We usually work with those. It's a whole lot easier. The idea of it is modify a selection structure. Modify our selection structure. Yeah, I guess one quick preview on the ease of this is I just dedicated a lot of time going over recursion and left like 5 minutes to talk about loops, the one we're actually going to use. It's so much easier. Modify our selection structure to an internal feedback. So it's not a full feedback loop like it is recursively where we're doing a feedback loop on the machine. We're just feeding back virtually inside our own piece of software. It's internal.
And that internal feedback, does it stay internal?
Our loop cannot leave our software.
Okay, it cannot leave ever.
Recursion, we're actually doing stuff like we finished that running that function every time, right?
Yeah.
So we did the complete thing. And a loop is a small enclosed thing that we keep in there. So
yep, so it stays within,
structures can't leave our software.
Yeah. It stays within the sandbox that it's within, right? And doesn't go out of it, right?
Yes.
Yep.
So here's our selection structure. We have ways that we can make easy comparisons. We've seen that, and most people take to that very, very quickly. The hardest part is getting it spelled out, because things where we have the compound ones like x is less than 3 and x is bigger than -8 to narrow down to a range. As humans, our first instinct is to carry that through and just combine this half, so x is less than 3 and bigger than -8. But the machine can't infer that part. So the biggest trouble most people have is remembering to spell that out in both places.
And then how would you do that for on a Raptor assignment, just having those
You
x's
just
less
solved my
than?
problem with my loop.
Oh, okay, you just set it up then?
Yeah,
And
that's
then
just
you
your
just
condition.
put
That's
in,
what goes in the diamond.
so it just
Instead
goes
of doing
within
two
that,
loops, I could have done
so it
one.
just goes within that loop and then, or in that
Yes.
selection, and then it's just, you put in an assignment or just those inputs.
Yeah, so like on your project, once you figure out that thing you were asking about earlier, how do you get those words saved? You get down there and say, you get down to like the subject of well, in poetry, it's the object. The primary object, which is the subject in a full sentence, but you get down to that section and be like, is the next word in the list a subject word? And if so,
Or is it a noun or a
here
verb?
next.
And
Yeah,
then one of them,
exactly.
so, and then you select noun, and then you go off of that, and then it's just like you get to pick your own path there.
Exactly. It's gonna take you a minute to figure out. That's why you have a month to do it.
That's a choose your own type of poetry venture type thing, where it's just kind of just like, you have a key phrase, and then it's like
Yeah.
you complete that sentence, and then it's like once you choose that, it's like, oh, you go on to the next part.
Yeah, so start working on it, start hitting those problems. We learn by tackling the problems and figuring them out. But the point here is we have this really easy way to make choices. Yes or no. So why don't we take one of our branches and just bring that back in? So if the answer is yes, we move on with our program. If the answer is no, we'll do some stuff over here. Maybe a couple assignments, another input or something. We'll do some things and then we'll check again. If the answer is still no, we'll do this stuff again.
And would I need to do that for my thing of just checking that again and going through the loop?
Probably eventually. This is the idea of how we repeat things. This one's easy to work with. And we just take those selection structures like we looked at. And one of our branches will come back around and ask and check again. So we just need to make some modifications before it checks again.
Sounds good. Sounds really good.
So loops are much easier to work with. These were invented in the early 60s. So most of our programming languages have them. There are still a couple programming languages that have been around for longer, and even some that are younger that we just didn't bother to put loops in because of what they're focused towards doing mostly. But we don't always have loops, but most of our programming languages have loops, which are really easy to work with.
Hey, Chris, I figured out that problem I had with my MO3-1 where I had two loops in there. I could have defined, instead of splitting into two loops, I could have just put and input greater than or equal to 100. That's what solved it. It worked. Version 1.2 is out
when
now.
I ran it, I didn't hit that problem. I used small numbers. I was using numbers I could calculate what the result should be in my head very quickly, as quickly as the computer could run it.
So basically, if you pass the first loop and then pass the first condition and then went on to the second loop, if you put in the first condition that wouldn't have passed the first loop, it would have still kept on running.
Oh,
yeah.
I didn't see that when I graded it, but I'm glad you thank you for taking the dedicating the time to figure it out. That's how we get better at these things, right? That happens a lot in software development. Sometimes we get it to work, but we don't know why it worked. There's actually some big things that we rely on. We know they work, but nobody can really explain why they work. Yeah, it was a typo when I went to make the code and it worked better than my plan. So I just went with it. There are actually several things, big things in IT.
It's magic. Yeah, some things that just liked it better.
Yeah, because humans don't think in the same way a machine processes. So sometimes little accidents from us turn out to be something way better for the machine. It's like, oh, well, we should probably go with that, even though we can't explain what it is. We know it works better.
Yeah.
So there's a few things like that, and sometimes sometimes we'll get it to work and not have a clue why it works. So if you encounter any of those, feel free to send a question my way. It's like, okay, the program did what it's supposed to do, but I have no idea why, and I'll try to explain it and clarify it. But some of y'all have already went ahead and used loops. They're a whole lot easier than this one. So let me start a new one here. It's this structure here. So we have a couple numbers. I'll set up a variable. I'll call it threshold. Let's say threshold is 35. Input, we'll ask the user for something. Enter a number. And I'll just call that user number. And then here's our loop structure. If I drag a selection in right beside it, you can see how it's just a modified selection structure. We took that no branch and fed that back in. So if our condition's no, we come back around and ask again. And there's two main categories of loops, and then each one of those categories has two subcategories. I'm always looking for the best words to refine that, but there's two groups, and then each one of those groups splits, has two types again. So it's like layers of binary sections. And with the picture, we can kind of see the two types best. And that's, when do we test? So we have pre-test and post-test. Because here's our loop. We can see because it makes a circle. So do we do stuff and then check our condition? Or do we check our condition first and then do stuff? Pre-test is, like it says, test first, versus post-test, where we test last. The difference is a post-test loop will always run at least one time, whereas a pre-test loop may never run at all. Our condition here, I just set up something threshold, and I'm going to say if user number is bigger than threshold, then we're done. So if the user gives us something like 50, okay, that's already bigger than threshold, we're done, so we can leave our loop and come over here and put some output afterwards. Finished with this trivial example. Moving on then. Because obviously in any of our programs, we wouldn't just jump to an output there, but there's probably still more programming to do. But I was just looking at the symbol, and after you all do some stuff with it over the next couple of days, then we'll talk about it and add some clarification points in on Monday. But if that's not the case, well, let's ask again. Oh, not output. Copy that. Paste it here, and that's below the threshold. Enter a bigger number. Something like that for a trivial case. So this would be a pre-test. This part may never run at all, right? We might never get into our loop. But if it if the user say gives us 50, we'll come down here, we'll test first, and 50 is bigger than 35. We're above the threshold, so we already exit our loop. But if the user gives us 7, we'll test, then come back around and keep coming back around until the user gives us a number that's big enough to exit the loop. If that was up here, that would be a post-test loop, because no matter what, this instruction is going to run one time, guaranteed to run one time. Then running more is dependent on what the user gives us. So that's where we choose between pre-test or post-test. Do you need that stuff to happen once? Does it have to happen once, or could you just bypass it altogether? So enter a number like 4. Oh, let me slow that down. Let's try that again. 4, enter a 4, goes through the loop. Oh, that's 4 is smaller than 35, so that's below the threshold. Go again. So 7, still too small. So this is almost a direct buildup from where an electrical feedback loops come in useful in electricity, right? If we need to build up a bigger charge, we keep checking, and it's like, okay, that's bigger than it was a second ago, but still not enough electricity to carry out the next step. So we need to build that up more. And it keeps building up until we finally get enough. This was just a generic example with no purpose, so except to look at what a loop looks like. So that time I entered 35, but 35 is not strictly bigger than 35. We need to actually be bigger than 35, like 35.1. And then it finally moves on to the end. So it just keeps going until our condition is met. A way to repeat things. Often with counters. So I'm going to move all this over to a subchart. Okay, subchart. First
Then you
loop.
could store a variable in a loop, and if a variable is met, then the loop would continue. Then you can have these different things happening.
Yeah, that's what I was going
Different
to do
instructions.
next time. So
Oh, okay.
that's what I was going to do for the next example. So let's do a classroom like example, like a grade book, right? Number of students, because we already saw how the selection structure to determine what grades people need. I think that was our example. Number of students, well, we're going to start with 0 because we need to count how many there are. And then I guess we'll just keep asking. How many students? Wait, I'm going to not do this example. That was going to lead back into just a question thing. So let me do something else. Let's say we know there's a certain number of things that need to happen. Workday, that'll be a good one. We know there's a certain goal, right? When we arrive at work in the morning, we're 0 hours into our day. And our workday is going to go until the number of hours has passed 8. It's at least 8 hours for the workday, right? So then, let me clear the console. This will be a good generic example. So then as our workday goes around, we'll do some work, which I'll just kind of print out to the console. And at that point, an hour has passed. So we can make our variable an accumulator and just keep adding stuff to it. So then set that workday variable to whatever was already there, plus 1 more. So our hours just pass 1 at a time. Our term for this is increment. This is something that happens a lot. We're going to increment the workday variable. Every pass through our loop, we increment it by 1. We also have decrement, which goes down by 1. Hopefully that example makes sense. Is that what you were talking about, Tyler? We have that
Exactly.
variable.
Yes.
It just keeps
Yeah.
counting until the end.
You're altering the variable every time.
Yes. So we run through here. Workday just starts, do some work, do some work, do some work.
Another day. Amazing.
Yeah. And as the workday slowly passes, stretches on and on, maybe get some lunch around this time, a snack, come back. And finally, okay,
And
then we're done.
cool.
Probably should have put an output at the end. Put an output at the end. The day is done. But the one thing you want to watch for with this is one of your biggest concern is an infinite loop. You made that comment earlier, Keegan, about a machine doing the same thing forever. What happens if we forget to increment our counter? It starts at 0.
It'll just keep
go
going.
until 8.
Yeah, we'll just, keep on going until it just, stops.
It just runs forever. Yeah, we call it an infinite loop. Usually that's not the goal. Sometimes it is, right? Like on a website, we might have a little animated logo we want to run the entire time.
This
And our
reminds
goal
me,
is an infinite loop, whether they're on our page for an hour or a year. We want that information for
what this
loop.
reminds me of? This reminds me of the what was the Shining? All work.
I thought the same thing.
Yeah,
That's
what was
exactly
that?
what it is.
The same thing.
All work and no
was the thing?
play makes Jack a dull boy.
Yeah,
Yeah,
so it
all
just,
work and no play make Jack's a dull boy. And there
so you want to avoid that usually.
That'd be a fun program to write, actually. Just do all the different, like,
Yeah, that's actually a common example for introducing
Really?
infinite loops.
huh, that's funny.
Print that for a while because there's no way for the machine to stop it. The machine will run forever and never complain about that. Which sometimes that's what we want, right? Looping animations are what always comes to my mind. If an infinite loop is what you want something that's just going to run forever. Don't be subtle about it. Like make your condition just say true or false, whichever one is appropriate to stay in the loop. That way, if anybody else ever looks at your code, they can immediately see your intention is to stay in that loop forever. Because sometimes we do want it. Usually we don't. In this class, we always want to avoid that. So whenever that happens, well, we have a stop button. In general, you have to crash your program. So let me do this in, look at this in Python. I'll open up idle and do this same thing in Python. That's handled on the cloud one, so I'm going to use the local one so I can actually make that mistake. So I'll create a variable called workday. This is going to do stuff for a while. Start it off at 0, and our keyword for Python will be while. And then we put a condition just like we did for an if statement, right? If some condition is true, then we do stuff. So while some condition is true, so in this case, workday is smaller than 8, then we'll print out, do some work, and increment our counter, which I'm going to run the infinite loop, and then we'll come back and increment the counter later. Let me go stick this somewhere to save. So now if I run this program, and this is a really, really common program, because usually these instructions are common problem, because usually these instructions here get all of our thought, right? We put all our focus and energy and efforts into putting the instructions we want to run happen over and over again, which makes that trivial step of incrementing our counter easy to forget, because our mind's in the focus dealing with the hard thing, not the easy thing. So you can see it's just running forever. Every once in a while we get a flash because it's changing. Whenever this happens, we have to actually kill the program. The program is still running. Do you want to kill it? Yes. I have to force it to stop. So you always want to remember to increment that. So workday is whatever was stored in workday plus 1. Now I always like to take a moment to pause and look at this whenever we get to increment. The fact that this statement works shows that our code actually runs right to left. As humans, Americans, we're used to English, right? Left to right. But this statement right here would not work left to right, because that would be an infinite loop going left to right. Going right to left, we take whatever was already in that variable, add one more to it, and then put that stuff over here. But going left to right, the way we as Americans would probably first try to think of that would be an infinite loop itself. Because we're going to assign workday to workday, but workday needs some more stuff, so that's a changing value, which means workday needs assigned to workday, which means workday needs assigned to workday, and we get an infinite loop if that statement goes left to right. So our code actually runs right to left. I like to always pause and point that out. But this one will eventually stop. Run that. Oh, yes, save it. So we'll start there. There's also for loops, but unless they did put it together in a sloppy way, we haven't seen enough to use a for loop properly in Python.
Well, okay, I have a question.
Yeah.
So, sometimes, or a lot of the times we want a result like I do, since it's logic and everything. But, with a few or like minor like programs out there, you want something like this, correct? So like, to prevent access, since I'm going to cybersecurity and everything. So you want to have something that sets up as a decoy so you can't like go into someone's system, correct?
That's one thing people use.
Yeah, so something like this where it repeats over and over again so you can't like access the important information.
Oh, no, that would not be good. No, an infinite loop wouldn't work because then they couldn't do anything on their machine either because the machine's busy running that infinite loop.
Yeah, but I mean, like, it's not on the user's end, it's on the other end of just setting up a decoy. So you can't like, go into the main system.
I don't know if an infinite loop would work for that. I might be misunderstanding some of what you're asking, but it would be obvious. It would make the fact that it's a decoy obvious.
Okay.
Because it's an infinite loop, nothing ever changes.
Because
Anybody that sees it is going to notice that nothing's.
I was just wondering. I was just like, my mind process was like, sometimes those endless loops could be a positive. So just of those type of things where it just it prevents.
Yeah, when you mentioned in the cybersecurity and infinite loops, an infinite loop would be a denial of service attack.
Yeah.
That's access this machine as an infinite loop, and then as quick as the machine can do it, it's just going to keep trying to access that server so that server can't do anything else.
Yeah.
So it's commonly used as an attack. But if I'm understanding what you're saying there correctly, it would make the decoy obviously a decoy. You would want your decoy doing things that made it look like it's a real computer.
Okay.
Right, you'd want your decoy switching back and forth between Microsoft Word and Excel all day, so it looks like somebody's sitting there doing work on that computer and that it's not fake.
I just thought there would be some instances where an endless loop would be positive instead of just like being negative.
Oh, there are instances where we use it as positive. Animations are what always brings some animated logos. They're just going to run forever until the programs manually crash, like closing a web page. We'd want an infinite loop there.
So just show it, like it.
Yeah, sometimes we do want an infinite loop, but usually not. Not for our class here. For our class here, we can definitely say that from now to the end of the semester, we will not want infinite loops.
Yeah, correct.
But there will be places where you want them. Right? The fact that the machine running itself is an infinite loop. Right? The BIOS is an infinite loop. Yes. In the chat room for like animated ads. We want that ad to run forever the whole time a human's around to see the ad. We don't want it to run once and stop. That might not get them buying our product. So there are places for infinite loops. The operating system is an infinite loop, right? We turn it on and it runs until we shut it down. Hopefully it runs on its own until a human shuts it down and it doesn't shut down on its own. So that there are places for it. But we will not see those places in our class. In our class, we want to use simple ones. So for the most part in Python, we'll use the while stuff, and notice how similar that looks to our if block. If workday is less than 8 or 9, print blah blah blah. It's coming on the end. I'm feeling less creative with the words. We'll just print something, but I wanted to point at this line. Notice that how much the while loop looks like the if loop, if block. So we just modified a selection structure so that it runs forever. Much easier than that recursion stuff we were looking at earlier. But that's the general syntax we're going to want to use for now with these to get started. And then we can run instructions repeatedly. Does anybody have any questions about those?
No further questions.
Okay.
Not here.
So that's our basic syntax. Tried doing some stuff with loops. We have an hour left today, almost an hour. It's an active subject. We learn by doing. As always, I'll be sitting here until 4:50 to answer questions. And I like when we can introduce stuff on Wednesdays and just see the basic syntax. So now y'all can kind of go play around with it, see what works, what doesn't work. While in the chat room it says is while similar to else. They're very different. So else goes with the we don't have an alter. I'll put it in a flow chart. I'm gonna look at a flow chart for this because in the picture.
Yeah, let's go. Let's talk about this just for like 5 minutes, and then
So our selection structures look like that out of the diamonds, right? So we would, when we relate that, we'd say this is the if side, and this is the else side. So we have two different ones. So here, the one in Raptor, our if is the true side, so that's where we're exiting, and our else, we can't, this branch is tied up, it loops back around. So we only have that one branch on it. Get all this ink out of the way. And a similar thing in Python with those words. If this is true, then we print that. And Python, the loop runs when it's true. So all we have is the true branch. We don't have a false branch. We don't have the false branch here. So there is no else branch. Does that answer your question, Johnny? So yeah, it's like we only have the one thing, the one option there. Our other option for the branch is tied up. Any other questions? Yes, yes. And while that condition is true, then we keep doing it.
alrighty. Everybody.
Oh yeah, I guess that came in as a private message instead of a public message. The question was, I should have mentioned that. Last two questions is a while loop like it needs is the same as the else, or while similar to else, and then is while. So while is for while needs to be true for the loop to run. Yes, yes on that. Sorry, I just answered the question. It's just saying it. Any other questions?
Nope.
Okay, I assume silence means no questions. So y'all have a great weekend.
Bye, everybody.
Let me know, and we will go over details about loops after you've had a little bit of time to play around with them. It's an active subject we learn by doing. For the next 50 minutes, I'll be sitting here ready to answer questions if you have any. Y'all have a great weekend.
Later.